Good morning. Today, rather than do what I said I was going to do, I want to go back and look at that starlight problem again. My internet's been out for several days, so this has given me an unfortunately large amount of time to think about it, and I want to talk about a more direct way of getting what we wanted to get in the previous video. In the previous video, we mentioned that we can easily write out the equations that describe the path of a light ray that just grazes the surface of the sun. It was this initial value problem, which for the rest of this video, I'm just going to refer to as the IVP. For a given theta value, we can use our numerical method to find out what the u that goes with that theta value is. U, of course, is the reciprocal of the arc coordinate. Once we know that, we can use the calculus techniques that we developed previously, which I'm just going to refer to as the mu and nu idea, to figure out the angle between the tangent vector of the path and what we could think of as the j vector. What we have done previously is we used our numerical method to solve this equation, this differential equation, and we kept an eye on what the u value was. When the reciprocal of the u value was bigger than the radius of the Earth's orbit, then we stopped. We saw that we had to make the number of steps rather large, not for reasons of accuracy, but because I didn't want to overshoot Earth's orbit very much. That made the calculation somewhat clunky, so today we're going to do this a different way. The initial value problem can be thought of as a function. It tells me what u is if I tell you what the theta is. This is not a very nice function, though, in the sense that it's not some little formula with squares and trig functions and stuff. It's a very complicated function, but even so, theta n produces a single u out, and then we can do the mu nu idea to get the deflection angle alpha over 2. So what is it that we want? We want to know a theta so that u of theta is 1 divided by the radius of the Earth's orbit. Let me re-express this a little bit. In the course on numerical methods, when we study solving equations, it's always some function of the independent variable, which is theta in this case, equals 0. Now that we have this written this way, I can use any of the standard methods. I could do the method of bisection, I could do the secant method, or what I'm actually going to do is I can do Newton's method. So we need to remember what that is exactly. For my reminder, I'm going to pretend that the name of the thing that I want to make 0 is f, and that the name of the independent variable is x. So I'm trying to solve f of x equal to 0. Some way or the other, we get an estimate, which I'm going to call x old, for the solution of our problem. Then we're going to go around in a loop a number of times. I'm going to take my old estimate of the solution minus a fraction. Upstairs is the thing that I'm trying to make 0, and downstairs is the derivative of that thing, both evaluated at the old estimate. Then we'll print out stuff, maybe the old estimate, the new estimate, maybe other stuff. Then we set x old equal to x new, and then we go around in our loop again. The thing that I'm trying to make 0 is u minus a constant. The derivative of u minus a constant is the derivative of u minus the derivative of a constant. On the other hand, because of the way we set our differential equations up, The y vector has components u and u prime. The number on the bottom of the fraction in our real method is going to be the second component of the y vector. Likewise, the u being the first component of the y vector says the top of my fraction, u minus 1 over the radius of the orbit, must be y1 minus 1 over the radius of the orbit. So if I keep all of this stuff in mind, when I change the names back to what I'm about to do, there should be no confusion. So, making analogs, I want to solve u of theta minus 1 over the radius of Earth's orbit equals 0. I know that the answer is somewhere in the range of theta equals 1.5. So it's not an unreasonable estimate to make theta old equal to 1.4. Then I'm going to go around in a loop a number of times, and I'm going to solve the initial value problem for y using theta old as the ending theta value. I'm going to say that my answer comes back in a vector that I'll call y new. And how am I supposed to do this? I'll use my numerical method, my extrapolated Euler method, for instance. Now, once I know y new, the first component of it is u, and the second component is du d theta. So theta new is going to be theta old minus the thing that I'm trying to make 0, evaluated at theta old, divided by the derivative of the thing that I'm trying to make 0. Then we will print whatever we're interested in printing. We'll set theta old equal to theta new, and then go back and do the next iteration. Except for the names of things, this basically is what we had written down before for Newton's method, keeping in mind that the function is u minus 1 over the radius. That's the thing that we're trying to make 0 here. Based on these comments, it should be a simple matter to modify our previous program to carry this plan out. So that's what we'll do. Let's look at how I can program this now. It's worth mentioning that in the program that I've now constructed, I don't actually make use of the T array, so I could have just left that part out. Also, yn is always going to be the array 1 divided by 6.96 times 10 to the 8, comma 0. Yn is never going to change in this program. From our previous work, we know that the answer is going to be somewhere near 1.5 radians for the theta. I'll use 1.4 as my rough estimate. Then, for as many steps that I've decided to do, I'm going to start at the initial point, theta equals 0, and theta old. I want to know the solution vector at theta old. Initially, that'll be the solution vector at theta equals 1.4. As I said, yn is never going to change. Y out will be the vector that consists of the numbers u and u prime at the value of theta old. Referring to the discussion that we just had, this is the step of Newton's method that I'll do to get theta number new. At each stage of the calculation, I will do the mu new thing to print out the theta value that I've just found, the corresponding u value, and the mu new shift value. Then, instead of x old being overwritten by the value of x new, it's theta old that gets overwritten by the value of theta nu. We end our loop and go around and do the next iteration, if there is any. Except for errors that come from the extrapolated Euler method, I should land on the orbit of the Earth, so I'm going to print out a couple of things to see about that. I'll remind myself what the radius of the orbit of the Earth is supposed to be. The first coordinate of the y vector is the u coordinate, which is 1 over the r coordinate. So I will print 1 over u out as well. And then I'm going to calculate the relative difference between those two numbers. The top of the fraction is how big the difference of the radius of Earth's orbit is minus the computed value for that number. I divide that by how big the radius of Earth's orbit is to get the relative difference. If this is approximately 10 to the minus n power, then we say that our calculation of the radius of the orbit is accurate to about n decimal places. In double precision, even in a perfect world, you can't expect more than 15 or 16 digits of accuracy, so this will give us a direct measure of how well our calculation is doing. So I compile my program. It asks me how many steps of Newton's method do I want to do. This time, no great number of steps will be needed. Using only 12 steps, at the end, I estimate that the total deflection is 1.7509618564299903 arcseconds. The radius of Earth's orbit is that, and the computed version at the end is very nearly equal to that. The relative error is about 10 to the minus 13 power. Considering that I could only expect under the best of circumstances an error of about 10 to the minus 15 or 16, this is quite good. An obvious question, though, is if I made the number of steps of Newton's method bigger, could I get a better answer still? I will allow 100 steps of Newton's method. Answer, no. So it looks like in this circumstance, about 10 to the minus 13 is about the best I can do. But as I mentioned, that's quite good. We conclude, using Newton's method, that the deflection is about 1.75096 arcseconds. This is in excellent agreement with the previous calculation. This gives us considerable confidence in our answer. In the next video, I'm going to do what I said I was going to do in the next video as stated in the previous one. I thought this was sort of fun. Until then, I hope everybody has a good day, and I'll talk to you again soon.